Okay, class, so today is lecture 11, where we learn about other proof techniques besides the direct proof. So the first thing we're going to learn about is called proving something using the contrapositive, but it's secretly still a direct proof. Okay, so we'll see why in a second. So recall the contrapositive, that's not how you spell that. Whoops. It's okay, there's no mistakes, only little happy accidents. Recall the contrapositive of an if-then statement or a conditional statement is what happens when you reverse the direction and you negate both statements or both pieces. So we saw this a long time ago, so you might not remember it. But then the other thing to remember is that they are logically equivalent. And that's the very useful fact. So just to remind you, let me give you an example. If n squared is odd, then n is odd. So this would be our P, but of course it's really not a statement, it's just a predicate depending on n, and this would be Q. So then the contrapositive would be, so I change it to Q coming first, but I negate it, and I also negate P, and I put that as that conclusion. So it becomes if n is not odd, well, not being odd is being even. If n is even, I'll just write not odd underneath it, then n squared is not odd either, aka even. So this is the contrapositive, and the fact that they are logically equivalent tells us that they are saying the same statement. They are the same statement. So if one is true, so is the other, and vice versa. And what that means is if I can prove one, then I automatically prove the other. So proving the contrapositive proves the statement automatically. So what you do is you look at the contrapositive and you just do a direct proof of that if it's easier. So prove it if it's easier to prove. And it's interesting because although they are the same statement, written differently, the statement and the contrapositive, very often one of them is much easier to prove than the other. Like in this specific situation, that is exactly what happens. So let's think about why. So let's suppose we try to prove the original statement. So the original statement is that if n squared is odd, then n is odd. So how would that go? I would let n squared be odd, and I would want to show n is odd. And now I'm just doing a direct proof, so all I'm going to do is expand upon what I know. So since n squared is odd, what can I do with that? I can say that n squared equals 2 times some number plus 1. But then, how do I get to n being odd? That's very hard, because I would have to eventually get to n being equal to 2 times something else plus 1. And I can't just square root, because how do you know that this is a perfect square on the right here? So it's really hard to do this in between stuff in this situation. So that's why this proof is a bit tough, but the contrapositive is extremely easy to prove instead. If n is even, then n squared is even. We've actually done that proof a million times. So what you can do is you can call it a proof by contrapositive if you want to say it in a very fancy way or something. But you could also just say proof and then say in the proof we will prove the contrapositive instead. Okay, so either way is fine. As long as you let the reader know you're doing the contrapositive. So we will prove the contrapositive. That means I'm going to let, well, first I should look at the statement, the new statement, the contrapositive. So that means I'm going to let n be even. And I'm going to show n squared is even. Well, I'm not going to do this proof because we've already done it. So you can finish the proof. But then the whole point is that this automatically proves the original statement, which was harder to prove on its own. Okay, so let's do another example. Where is my paper? Here it is. Okay. Okay, so here's another one. For any a and b in the real numbers, so aka for any two real numbers, no matter what they are, if a is not 0, oops, 0, and b is not 0, then a times b cannot be 0. So this is just saying if you multiply two non-zero numbers together, there's no way the result could ever be 0. And this is actually a bit tough to prove in this form. So what we're going to do is we're going to prove the contrapositive. Now we do have to be a little bit careful here because the way it's written here, we sort of have this stuff coming before the if-then. So we're just quantifying the a and b before we put them in the if-then statement. And if you want, you can like try to write it a little differently, which is you could say like if a and b are non-zero real numbers, so basically I'm taking the for all and I'm putting it inside of the if, and then I'm anding it, and a is not 0 and b is not 0, then a times b is not 0. But when you do that, it's sort of weird when you do the contrapositive because the then doesn't have those quantifiers, doesn't tell you about what a and b are. So it's better to just leave the for all in the front. So for all a comma b in the real numbers, we're just going to do the contrapositive of the if-then part. So if the conclusion doesn't happen, so that would mean a times b does equal 0, then the hypothesis doesn't happen. So then, let me write it like this, a negation symbol. A is not equal to 0. And let me write the and with the symbol to remind you how negating an and works. So when you say that it's not true that a doesn't have to be 0 and b doesn't have to be 0, what you're saying is that a can be 0 or b can be 0. So what we're using here is this De Morgan's law. Oops. So we are distributing the negation through, so we're negating the fact that A is not equal to 0 to say it is 0. Then we're turning the and into an or. Then we're negating the fact that B cannot be 0 by saying it is 0. That's what we're using here. Okay, let me put it back in word symbols or. So the quantifier at the beginning is not really getting negated. I'm just doing the contrapositive of the if-then statement. Because it's not in the if-then statement in the first place. Now you could, again, rewrite it like this, and then you would have to think of it again a little differently maybe, but this is fine. Okay, so the point is we are going to prove this guy. So I'm going to let the hypothesis be true. So now it's a direct proof of just some brand new statement that happens to be the same as the old statement. So I'm going to let A and B be real numbers. And I'm also going to let A times B equal 0. Then I'm going to show that either A equals 0 or B equals 0. So how can we go about this? Well, the then part, the thing I'm showing is an or statement. So this is true as long as what? As long as one is true. I don't need them both to be true. So we're going to pull a little trick here. I don't need them both to be true. So I'm going to imagine a case where one of them is false. So I'm going to add an additional assumption. So next, suppose A is not 0. So this does not hurt the proof. This does not make it an incorrect proof, adding this assumption, because I'm not assuming that the conclusion is false. I'm just assuming one of the two or statements is false. And that is okay, because what's the alternative? If it was true that A was 0 already, well, the proof would just be done, because that would mean that the or statement is true. So that would mean that the conclusion has been proven, that either A equals 0 or B equals 0. So those are the only two possible situations that could happen. A could be 0 or A could not be 0. If A was 0, the proof would be over. That would be done. So I'm really just seeing what happens if A is not 0 and seeing that still things work out. Okay, so suppose that A is not 0, then what can I do? Well, then I can divide by it. So I can say that B equals 1 over A times 0. Well, if A was 0, I wouldn't be able to do the step because I wouldn't be able to divide by it. But now, since I know it's not 0, I can divide by it. And 1 over A times 0 is just 0. So I get B equals 0. So I have proven that the other thing happens when the first one doesn't. Okay. So if instead A were 0, that's the other possible situation, then this also proves the statement true. So the idea is that in either case, A 0 or not 0, doesn't matter, the entire conclusion, A equals 0 or B equals 0, is true. So either way, A equals 0 or B equals 0 is true. So this ends the proof. So what we've done is we've proven the contrapositive, that if A times B equals 0, then either A or B has to be 0. And that's the same as the original statement, which is that if you take two non-zero numbers and you multiply them together, the result will not be 0. Okay, so again, a proof by contrapositive is really just proving the original statement by proving the contrapositive still in a direct way. So it's not really a new technique so much as it is a rephrasing of the original statement and then a direct proof of that statement instead of the original, just because it's easier. What I do want you to notice is that the contrapositive in this situation, why can't I stop the scroll? There it goes. Note, this contrapositive is of the form, so it really looks like an if-then, where the then is an or statement, right? So this looks like if something happens, then either this or this happen. So this contrapositive is of the form if P, then this or that. And a long time ago, we actually showed that this was the same as saying if P happens and Q doesn't happen, then R happens. And that is actually what we've done to prove this statement, because what we've done up here is we assumed P and we assumed not Q. This would be our Q in this little writing down here. AB equals 0 implies that A equals 0 or B equals 0. And what we've done to prove this is we've said, okay, let AB be 0, but also let A not be 0, and then we'll show B is 0 as a result. That's what we did. So the fact is that these are logically equivalent, and what that means is I didn't even have to really do this extra explanation at the end. I was just doing it because I hadn't revealed that we were doing something else secretly. So using this equivalence comes up a lot, but we don't really call it its own technique. We just naturally use it a lot. And the technique is that if you're proving an if-then, and the then has an or, like this guy does, what you're always going to do is you're going to pretend that one of the two in the or is not true. Because like I said, if it was true, then you would already be done. The conclusion would already be true since it's an or. So you're going to pretend it's not true and make sure it's that the other piece of the or statement still happens. Okay. All right, so I'll keep pointing that out when those types of proofs show up. But for now, that's it for contrapositives. Next, let's talk about something else, constructive proofs. So this is not really a technique so much as it is just pointing out something that happens a lot. So we often prove a there exists statement. So like there exists something that does something else. We often prove statements like that by constructing the thing that we want to show exists. That makes sense, I hope. You want to show something exists, so you just find it, you just construct it, you create it to make sure it exists. So in a situation like this, you might do that statement. Here's a statement that this works for. If A comma B comma C are real numbers, and A is not 0, then the equation AX plus B equals 0 has a solution. So in this situation, I just said it's like it often shows up in a there exists statement, but then I didn't write the word there exists in this statement at all. Well, oftentimes you can think of the same statement in many different ways if you're just very careful about it. So really, this is a there exists statement. You could think of it as the same as this. You could think of it as for any a comma b comma c in the real numbers where a is not 0. You could think of this as a multiple quantifier. For any a, b, and c in the real numbers where a is not 0, there exists an x in the real numbers such that ax plus b equals 0. So oftentimes the quantifiers are hidden because they're hidden by context. And also they're hidden by the fact that an if-then statement can almost always be thought of as a for-all statement. Okay, so that's something to think about for another time. But for now, let's just try to prove this statement. So this is a constructive proof. You wouldn't really say out loud that it's a constructive proof, you just do it. But it's a constructive proof because I'm claiming that this guy has a solution, and I'm just going to find it to prove that it has a solution. Or in other words, I'm claiming that there's a number solving this equation, and I'm just going to find it to show that it exists. Same idea, two different ways of thinking about it. Okay, so here's the proof. It still is an if-then, so I'll let the if stuff be true. Let a comma b comma c be real numbers with a not 0. Okay, and then I'm going to show ax plus b equals 0 has a solution. So here it is. Well, I know how to solve linear equations. Whoops. Why did I write 0? Sorry, it was supposed to be c the whole time. No, geez. You must have been thinking, why did he write a, b, and c, and there's no c in the equation? Well, I hope you saw that earlier than me. Okay, this should always be a c. Okay. And one more c right here. I give myself a c for this example. Okay, so we're going to show that ax plus b equals c has a solution by just saying exactly what it is, by finding it. So of course, you would find it using scratch work, but I can do this in my head. So then x equals c minus b divided by a is a real number. Why is it a real number? Well, because a is not 0, and so there's no risk of dividing by 0. So this is a real number, and it does exactly what it should do. If I plug it in for x here, it will give me c, because I'll get c minus b plus b equals c. So it's a solution. So I've shown a solution exists by just naming the solution. So that's okay, it's kind of boring. That's just like exactly what you expect you should do. And what you might think is like, yeah, any time that you claim something exists, you're definitely gonna have to find it to prove it exists. So it's kind of like stupid to name it something fancy like a constructive proof. Well, it's not stupid because the only reason we name it like that is that there are sometimes non-constructive proofs, and they are much more interesting because you probably haven't thought of them before. So what happens here is we prove the existence of something. Existence, how do you spell that? Yeah, I think, of something without actually saying what it is. This is much weirder. I hope that you see that it's much weirder. And because it's much weirder, it's hard to have examples offhand that are not too hard and that involve things you've actually seen before. So I'm going to do an example, and you've probably seen it in calculus, though you've probably long forgotten ever seeing it, so you probably think you never saw it, but I guarantee you did. So here is a wonderful statement. The equation x cubed minus x plus 1 equals 0 has a real number solution. So I got kind of lazy here. I didn't put it in the form of like an if-then, and I didn't say there exists, but it really is another there exists statement. So try yourself to think of it in that way. But what I'm really doing is I'm proving that a number exists solving this equation, a real number. And I'm not going to solve the equation because it's a cubic. I don't know how to do it off the top of my head anyway. It's not a quadratic, so I can't use the quadratic formula. And I don't know how to factor this off the top of my head, if that would even work. Okay, so we're not going to solve this. We're going to use some calculus in our proof. And then I know it's been a long time, but I think we can handle it. So let's see what we can do here. So in calculus, we often study functions. So the first thing I'm going to do is I'm going to think about x cubed minus x plus 1 as a function of x. So I'm going to name f of x the function, which is just the left side of this equation. So then solving this equation is just setting f of x equal to 0. So hopefully you can see that. All right. And now what we're going to do is we're going to remember function land over here in the scratchwork zone. We're going to remember some cool facts about functions. So functions can be continuous, and that's like when it's the best. So what does continuous mean? Well, for our purposes, it means like you don't pick up the pen, but don't tell that to any mathematicians or else they'll yell at you. It's much fancier than that, but for now, just think about it in that way. So if this is a function and it goes from negative to positive, like this one, like this drawing, then because it's continuous, it has to cross the x-axis, aka the 0 line. And what that means is that when it crosses it there, whatever number that is, I don't know what number it is, but what I do know is that when I plug it in, I get 0. And I know it has to exist because the function is continuous. It doesn't just jump over the 0 line. This is the idea. So if it jumped, then sure, it wouldn't exist necessarily, but that's not happening for continuous functions. Okay, so that's the picture I want you to imagine as we go through this proof. All right, so notice some stuff. Notice that if I plug in -2, go ahead and calculate that if you want, you'll end up with -5. And if you plug in 0, you'll get 1. So now let me update this picture a little bit for this specific function. So when I plug in -2, I get -5. And when I plug in 0, I get 1. Now, the idea is going to be this function is continuous, so I got to get from here to there somehow. Maybe not exactly like that, but somehow. That means I got to cross the 0 line. So I got to cross this magic 0 line somewhere, so why not there? And that's going to show the existence of something. Okay, so here we're making a couple of jumps in logic though, because we're not proving calculus from the ground up. So we're just going to remember that this kind of function, because it's a polynomial, is continuous. I might not know how it looks, but I know it's continuous, meaning I know I don't have to pick up my pen when I draw it. So since this is a continuous function, it must go from this point -2, I plugged that in, I got -5, to the other point, 0, 1. It must go from there to there continuously. Thus, there must exist an x value. I don't know what it is, but I know it exists, and I'll just call it C, between the two things I plugged in, -2 and 0, such that when I plug it into the function, I get 0 to pop out. That's exactly what this picture is displaying here. Because I go from here to here, I got to cross somewhere, so that C is where I'm crossing 0. So that means when I plug it in, I get 0 as my answer. So thus, there exists a real number C such that, well, f of C, that's just this function with C plugged in. So C cubed minus C plus 1 equals 0. So this is the end of the proof. I've proven that there is a real number such that when I plug it into this guy, I'll get 0. I don't know anything about the number except that it's between -2 and 0. So this ends the proof. So an addendum, I guess, in addition to the proof, is, I just want to say all we know is that C is between -2 and 0, but we don't know exactly what number it is, just that it exists. So this is why it's a non-constructive proof. So if you're wondering what all this stuff was that you learned in calculus, you can go Google the intermediate value theorem. So all we're using is the intermediate value theorem, which you learned about a long time ago and you've probably forgotten by now. But that's what this was all about. Okay, so that's going to be it for today. The main technique to remember is the contrapositive, proving stuff by rewriting it as the contrapositive. We're not going to name constructive or non-constructive proofs very often. They just sort of happen. Okay, so that's the end of today. See you next time.